In this video we will look at confidence intervals or interval estimation. Hopefully we'll take the concepts and procedures or methods that you learned in the previous units and put some of them together and now do some statistical inference. We'll take a statistic like a mean and we'll expand on it. We'll not just use that point estimate, but we'll use what we know about sampling distribution, probability, and the mean and standard deviation, and put those together and construct then with so much percent of confidence a interval that we believe that the true mean or true proportion, depending on the parameter that we're looking at, is in that interval. So we'll start with the mean, and we'll look at a case where, and that's one of the biggest issues of statistical inference, is just getting down what you have and what you don't have. Well, obviously we don't have the parameter, so we don't have the mean or we don't have the proportion, and typically we don't have the variance or standard deviation. However, sometimes it's believed to be known, and so we go that route. We actually won't look at it in this video, just in the interest of time, but it is discussed in the notes and in the book, and you can easily apply it, like in the way that we do these problems here in the video. So what we'll do in this particular example is start with a small sample size. I actually have 13 observations. There's 16. I randomly sampled 16 from a total of 214 countries, and I believe territories are also included in there, and from the World Bank. And there's obviously various data you can see that is provided. We'll look at this health expenditures per capita here in US dollars, and what we'll do is construct a 99% confidence interval for a country's health expenditure per capita, again in US dollars. So if you follow the 4 steps that I present to you in the notes, and I'd like for you to do that, you would identify the alpha first. And so if at 99%, then it's just 0.01. And then start calculating. Now you may be given the raw data, and you may have to calculate X bar and S yourself, and that's the case here, although I was able to use Excel, but you also be able to do this by hand and show that to me like you did had to with the in the first exam. So we calculate the mean and standard deviation, and then with the sample size of 13 and the standard deviation of 1151, I can calculate the standard error, because that's just S over the square root of n. Now the question then, and here's one of those other things that you have to see what you know and don't know, is should I use the finite population correction factor? Well, it's perfectly fine to. You're not going to be wrong using the finite population correction factor. So if you have cap n, if you have the population size, that's fine. Just go, if you want to use it, that's perfectly fine. But if it's we've said in the notes that if the ratio of sample size to population size is 10% or less, then it really is not going to change the standard error that much. So I'm just going to go ahead and ignore it here. And because I have a small sample size and sigma is unknown, in this case I don't know sigma. I calculated the variance and standard deviation from the sample, so I don't know the population standard deviation, so I have to use a t. Okay, and so I can either go to the t table, or I can use this t inv dot 2t, and so you can use it that way, but also be able to read the t table. So at 0.99 and 12 degrees of freedom, you get 3.0545. Okay, so either way works. And so now you've got everything. You've got all the pieces to the puzzle. You just then take X bar 835 plus the 3.0545, the reliability factor, times the standard error. Okay, so it includes all those. Same for upper bound, but now you're going to add the reliability factor times standard error. And so now you have your lower and upper bound. Okay, and so now make a conclusion about that. I am 99% certain the interval 140.6 to 1810.2 contains the true mean health expenditure per capita for all countries. Okay, and you're pretty much done then. Now, you might see this number here and think, wow, you can't have negative expenditures. So if you wanted to, you could put 0 there. I just went ahead and used the numbers that were found here, but it would, for this particular example, it would be okay to certainly okay to put 0 there, since it would make more sense actually. Okay, but that's the thing that I wanted you to see though here is, in this particular example, you really have a pretty large margin of error, or precision's not too great here. Okay, precision would be the difference between the upper bound and lower bound. The margin of error is half that. Okay, and so what that means is that if the true mean is actually in this interval, and we're 99% certain that it is, then I could still be $975 off. And the question would be, is that very telling? If you were making decisions on funding and things like that, then would that really be all that helpful? And so if it's not, then we have to do something about that. And one way to deal with it is obviously take a larger sample, and that would help reduce the standard error and give you more precision here. And then when it becomes more precise, this might shift. This might tend to shift up or down, closer to where the mean actually is. Now, with one single sample, you never know. But given what you understand about the sampling distribution, you know that the likelihood is better as sample size increases. So that's a small sample confidence interval for a mean. And then we'll do a large sample confidence interval. But just, again, follow the 4 steps here, and if you create that structure, you should do just fine. The large sample, then, using the same World Bank data, but in this case we'll use a different variable. We're going to use the birth rate. So let's construct a 95% confidence interval for a country's birth rate, and this is per thousand. So that's actually this variable here, and so after step 1, where I identify alpha as 0.05, it turns out I have 48 observations, okay, that actually we have data available for birth rate from the total sample that I took. So I end up with 48 observations. That's 47 degrees of freedom, and we have, it turns out, a mean, or X bar, of 21. Okay, and an S, standard deviation, of 9.743. Okay, so both of these are statistics. We don't know sigma, we do not know mu. Okay, so we have X bar and we have S. So we really have another t distribution here, like we did with the small sample. Okay, and this video assumes that you have looked at the notes involving t distribution. If you haven't done that, you probably want to hit pause and make sure and look at both the notes and the textbook on t distribution. But so we do have a situation where it's a t-distribution because sigma is unknown. So we'll get back to that in a second here. But let's compute the standard error. That's just s over the square root of n. But we do have a situation where the sample size relative to the population is fairly high. It's over 20% of the population. So we're going to go ahead and include the finite population correction factor. Remember, that's population size minus sample size divided by population size minus 1. And I made a mistake here. So we're just going to do that on the fly. Okay, so it's going to reduce the standard error by a factor of 0.88. So our standard error becomes 1.2415. We've got, as I mentioned earlier, the t-distribution because sigma is unknown. However, because of 47 degrees of freedom, we can approximate with the z. So there's not, if you go to the t-table, here we go. Okay, go to the t-table. Hopefully, doing too much thinking right now. There we go. And you see that there's not 47 degrees of freedom in the textbook t-table. Okay, so some people might try to interpolate these two values. Some people will go down to 40 to be conservative. Okay, but a lot of people, anything over 30 degrees of freedom, they say, okay, the z is a good approximation, a decent approximation. I'm in the wrong worksheet. There we go. And so that's what we're going to do here. So we've got a reliability factor then of 1.96, because if you go to the z table to approximate, if at an alpha of 0.05, you've got to split that up, so 0.05 divided by 2, so you're going to have 0.025 on the tails. So that means we'll look up 0.4725. And sure enough, there's the 1.96 there. Okay? And so that's what we're going to use to approximate. It's not perfect. In fact, if I wanted to be more exact, could do that, and that's the actual number. So I'm a little bit off there. 2.011. I'm going to use 1.96. So obviously, if we're in Excel, this is the way to go. But we're not always going to be in Excel, and we're going to have to in 263 and some other cases. You're going to use the z to approximate. So even though we have Excel available to us, in your situation, we are still going to learn to do it this way. So using 1.96, we now have all the pieces to the puzzle. We have x bar 21 plus and minus the standard error times the reliability factor. Okay, so 21 minus 1.96 times 1.24, and you get 18.52. 21 minus 1.96 times 1.24, you get 23.39. Okay, so I'm 99% certain the interval 18.5 to 23.4 contains the true mean birth rate for all countries. And so now you've constructed confidence intervals for means. Obviously, we could just go to our data set, and by the way, this is for 2010 data, and it turns out that our true mean of those 214 countries and territories is 21.5 for the birth rate and 1009.75. So we actually, we do include the mean. The problem is this is not too impressive. Its precision is not too great, and this is better. Okay, but obviously they both turn out to include. We won't know that when we only have a sample and we don't have the population. We're only going to have a sample, but you can see that from your work with sampling distribution that at 99%, 95%, you're typically going to have a sample when you construct the interval that it should contain the true mean. Now when you start to get to 90%, 80%, things like that, then it's not going to be quite as likely, and that's why we say confidence, or 99% confidence, 90% confident, so forth. We actually, or one of the reasons we say confidence and not probability is because it essentially already happened. Okay, so the interval either contains the mean or it doesn't contain the mean. So there's really not a probability. The probability is either 1 or 0. Okay, so we kind of stay away from that and talk more in terms of confidence. If we were to do this many times, we'd feel confident that 90% of the time it would contain the mean, or 99% of the time it would contain the mean. Well, one other topic we looked at with confidence intervals was, well, what's the appropriate sample size? So let's go back to the small sample case where we're looking at healthcare, and I had a pretty wide interval. And so it says here, what if preferred maximum confidence interval width for a 99% confidence interval for the mean per capita expenditure on healthcare by all countries was $500? Also, assume the population standard deviation is 1,500. Okay, now we could have just used the sample. We could also use this right here, 1151. Okay, so we have different options here. Since we had a small sample, some people might say just use the information from that small sample. But we're going to use 1,500. We're going to assume that's what we got. We got alpha 0.01. So now we can't use t. There's no way of using t. So whenever we're doing a sample size determination, it's got to be a z, because t is dependent on degrees of freedom, which is in this case dependent on n. Well, we don't know what n is. We're trying to find n. So we have to use a z. And so if you go to the z table, or if you use the norm.s, but this gets a little complicated because they don't do two-tail with norm.s. So just go to the z table, and you would find let's see, 0.99. I'm sorry, 0.4949 versus 0.4951. We want 0.495, so 2.575. If we look up here, 2.575, be right smack in the middle there. So, but I went ahead and used a little more exact. But anyway, 2.575 would be perfectly fine. And so we've got an n here then of where you have z squared times sigma squared divided by, and here we want the it says confidence interval width of 500, so e has got to be half of that. E is the tolerable error, and so what do we want the most margin of error to be? Well, then that's half the confidence interval width, so 250. Okay, so then you're dividing by 250 squared. Okay, now we have 214 total observations, so we should make the adjustment then. And so we take, this is kind of our n sub o. So again, this assumes you've looked at the lecture notes on sample size determination. So you take the 238.85 or 86 times the population size, 214, divided by the 238.86, the original calculated n, plus population size minus 1. So now that's going to reduce it from 238, or around 239, to 114. Remember, always round up, so that you meet your requirement. So we have a n taking into consideration the population size of 214, then of 114. So notice we have to take quite a bit relative to the population size to get to this interval width, or this tolerable error. Okay, so remember we were at an error, margin of error of almost 1,000, 970 something, I believe. To get it down to 250 takes quite a bit more information, quite a bit more number of observations, and you have to decide whether that would be worth it. Obviously, with this kind of data set, it wouldn't be that hard to do, but there's always a cost, and each additional observation in a lot of cases, especially if you were doing interviews and things like that. So it's important to to get a good handle on the number of observations that you need. Now notice here that, this n even turned out to be greater than 214, because it had, when we first calculated n, there was no indication of any restriction in terms of sample size, or in terms of population size. Okay, so once we do this here, then we need to make that adjustment to factor in the population size. So that's confidence intervals for mean and sample size determination for a mean. We'll stop with this video, and then we'll do a new video on confidence interval for proportion and sample size determination for proportion. Let me know if you have any questions.